In this problem, we need to evaluate the following four limits. The first of which is the limit as x approaches infinity of the function e to the x. Recall that e is approximately 2.718, so this question is basically asking if you had the function f of x equals roughly 2.718 raised to the x power, what would happen as you plug in successively larger and larger values of x? So I'm going to make a table of values over here. The first column will be my input variable x, and my second column will be the actual function f of x equals e to the x. And I want to plug numbers in like 1, 2, 4, 6, 8, 10, and 12 should suffice. Now let me go to my graphing calculator, and I'm going to press y equals. I'll press second and then the ln key for e raised to a power, and then type in x. Now I want to set my table up by pressing second window, and I prefer to go down and change the independent variable to ask, and then I can just type in the inputs as I see fit. So now that that's set up, if I press second graph, which is the table feature, I can now type things like 1. Now when I press 1, you're going to get e to the first power, which is that 2.71828, and it does do some rounding there since the columns are not very wide in the calculator. And then when I type in 2, you're going to get 2.718 squared. So obviously, the higher the exponent, the bigger the output's going to be. Now I'm at about 7.4, rounding to the first decimal place. Let me type in the rest, 4, 6, and as you can see, as I plug in successively larger and larger values of x, my function values are getting very, very large. They go from 7.4 to about 54.6, then roughly just 403, 2981, etc. You can also press zoom 6 to see a rough sketch and verify as you trace to the right, meaning as x gets larger and larger and larger, you can see the graph going up representing larger and larger output values as well. So both from the table of data and the graph, you can tell as x gets larger and larger without bound, your function values will get larger and larger without bound. Sometimes we say, since the limit does not come out to be a real number, comes out to be infinity, sometimes we say d and e, which represents does not exist. But in the case of this problem, we want to communicate that the function values did grow without bound, but they were always positive. So we'll say that the limit is equal to positive infinity as opposed to negative infinity, which is what we'd write if the numbers were growing without bound in the negative direction. Now let me use this table for the next example, because the next example is very similar to this one. The function is e to the minus x rather than e to the x. If you remember your exponent rules from college algebra and make the problem of 1 over e to the x and express the function without the negative exponent. So now what's going to happen is, now that we have this function 1 over e to the x, this column will be basically 1 divided by the numbers in the previous problem. So for example, this one will be 1 divided by 2.718. The next one will be 1 over 7.4. The next one 1 over 54.6. You get the idea. But since the numerators are fixed to be the number 1, right? All my fractions have 1 in the numerator, and my denominator is growing without bound. That's what we saw in the last example. Then you should note whenever your numerator is a fixed constant and your denominator is growing without bound, the outputs should get closer and closer to 0. You should get a smaller and smaller output. And you can see that in the graphing calculator. As a second function, I will type in e to the negative x. Make sure to use the white negative key as opposed to the gray subtract key. And I'll go to that table again, and it'll automatically fill that out. So apparently, 1 over 2.718 is 0.37. 1 divided by 7.4 is 0.13, but the idea is as x gets larger, you see the y values get smaller and smaller. In fact, let me copy some of these for you. Rounding the values, this was about 0.4, this was about 0.14, this was about 0.018, 0.002, and then when you plug in x equals 8, the number gets so small that the calculator starts expressing it in scientific notation. Notice that it says 3.4 e negative 4. So 3.4 e negative 4 means you are to move the decimal place to the left 4 times, and that would be 0.00034. So you can see the numbers are getting smaller and smaller, and then I will skip the rest because it's quite obvious that the exponent here becomes more and more negative. E to the minus 5, e to the minus 6, which means you're moving the decimal place to the left even more. But the basic idea is you have a fixed numerator, your denominator is getting bigger and bigger and bigger, and when you divide it by a big number, the result is a small number. So I'm going to say as x gets larger and larger and larger, my y values get smaller and smaller and smaller. They get close to 0, but never actually reaching 0. So the limit is simply 0. You can see the graph by pressing graph. You see that on the red graph, if you trace to the right, that the y values get smaller and smaller and smaller, right? This graph starts up high, around 10, and then gets smaller and smaller, apparently almost reaching the x-axis, which would have a y value of 0. Our third example also involves e to the x. In fact, it involves e to the minus x. But in the last example we saw, the e to the minus x was approximately 0 for large x values, meaning the larger the x value you plug in, the closer e to the minus x would be to 0. So what's happening is, it's important to notice that we are actually plugging in larger and larger x values. X approaches infinity, meaning x grows without bound in the positive direction. So what's going to happen is, as shown in the last example, e to the minus x is going to get infinitely small. In my denominator, I'm going to have 4 plus a number that is essentially 0. So my guess is what you're going to get, since this number is approximately 0, then your denominator is going to be approximately 4. So you should get roughly 1/4. Now that's just a conjecture. Let's look at the table of values to see if that's true. And of course my calculator will give me the decimal equivalent to that, which is 0.25. So I'm looking to see if I get outputs of the function 1 over the quantity 4 plus e to the minus x closer and closer to 0.25 as x gets larger and larger. So I'm going to go to my calculator, go to my y equals. Let me just clear the previous two examples now, and my first one will be 1 divided by, since my calculator is not giving me the pretty print form of this fraction, I'm going to put parentheses to let it know that everything I'm about to type will end up in the denominator of my function, and that should be 4 plus e, so press second ln, to the negative x. I'm going to right arrow to get out of the exponent position and cap that left parenthesis off with a right parenthesis. And I'm going to go second graph, which is that table, and still has the desired x values. And as you can see, let me scroll over to the y values here, you can read them from the bottom. You're not quite 0.25 yet, you're at 0.23 if I round, then 0.24, then 0.24886, 0.24985, and then I get 0.24 followed by 2 nines. Now it looks like we're going to get 0.25, but that's just because the calculator is rounding it because your table has columns that are pretty narrow. But when I actually go down, you'll see that instead of having 2 nines, I get 3 nines now. And then finally, I'll get 4 nines. So the larger the x value I plug in, the closer you will get to 0.25. Your calculator will eventually have round-off error. So for example, if you skip to something like 20, I'm guessing that it's going to actually round it to exactly 0.25. Nope. You just get a lot of nines, but there is a number for which you will exceed the calculator's ability to calculate that accurately. There it is. If you plug in x equals 50, it is now actually rounding that to 0.25, but it's important to note that you never actually reach 0.25 because e to the minus x doesn't actually reach 0, right? If e to the minus x actually hit 0, you literally would have 4 plus 0 in the denominator, and you would literally have 1/4. So I don't feel the need to copy down the numbers in the chart, but you get the idea. As x grows without bound, right, they get bigger and bigger and bigger in the positive direction, your outputs of the function given approach 0.25. So just to be complete, this limit is equal to 0.25. If you want, you can graph this by pressing graph, but remember we're on the standard window, and our y values are really small. In fact, they got close to 1/4. So you'd have to go to your window if you wanted to see this graphically. So maybe make your y min 0 and your y max 0.5, and then we're looking for 0.25, which would be in the middle of those two values. Now if I regraph it, you can see that the function values are actually growing, but then level off to this horizontal line right here. And for effect, as a second equation, you can graph y equals 0.25, and if you graph that horizontal line, at least visually it checks. It looks like the function values on the blue curve approach the red. In fact, so well that the red line actually covered up the blue pixels. So anyway, that was example 3. We have one more example to do. Our last example is 1 divided by the quantity 8 plus e to the x. And since part of the function is e to the x, I copied the table from our first example that had x increasing without bound in the positive direction, and we noticed that the outputs grew without bound. So the answer to that one was infinity, or you can just think of it as a large number. So what you're doing in this example is, as x gets larger and larger, your fraction will be 1 divided by 8 plus a very large number. How large? Well, as large as you want it. It goes to infinity, right? The larger the x value you plug in, the bigger e to the x will be. So e to the x becomes as large as you want. Adding 8 only makes it a little bit even bigger yet. So what you have is a structure that's 1 over a really huge number, as big as you want. And so what happens is the same thing that happened in the first example. Whenever you have a fixed numerator, like in this example 1, the larger your denominator gets, the closer the fraction gets to 0. So for example, if I made a column and had the function 1 over the quantity 8 plus e to the x, what you'd have is 1 over 8 plus 2.718. Let's just round it to 2.7. Then you would have 1 over 8 plus 7.4. You get the idea that adding the 8 really actually doesn't make the denominator that much bigger once you get to numbers like 162,000, right? This one's going to be 1 over 8 plus 162,755. So the structure you have here is the same as the first example, where you have a fixed numerator. It's always 1. And your denominator is getting very, very large. So you're going to have your outputs of your fractions getting closer to 0 as your x values get larger and larger in the positive direction. So I can tell you already that this is going to be 0, much like the first example. But to convince you further, let me go to my calculator and clear that second one. And this problem is very similar to the last example. So I'm just going to change that to an 8. And I'm going to delete the negative key. So there's our function for the fourth limit example. And if I go to my table of values, you should see as x gets larger and larger in the positive direction, indeed your y values get smaller and smaller, 0.09, 0.06, 0.016, 0.002, and then you get that scientific notation again. In fact, look what happens when you plug in 50. You get 2 times 10 to the negative 22, which means you need to move the decimal place to the left 22 places. That's the equivalent of 21 zeros, followed by the number 2. So you can see, at least arithmetically on the table of values, that it's getting closer and closer to 0. If I was to zoom 6 this, you should see that the y values get really, really small. But again, since they start out small, it's more appropriate to start with a y min of, say, 0 and maybe a y max of, say, 0.5. And let me regraph that. So you can actually see that the graph isn't the x-axis. It starts higher, but then dives right down and gets closer and closer. And if you need to change your window so that the x-max is bigger, like 50, to see further to the right to convince yourself that it does actually stay right down there as part of the x-axis. So I've done all 4 problems using a table of values, and I've done all 4 problems graphically, but you can kind of get the idea that you can do all of these just using some number sense.